Good morning, everyone. Language models don't just happen. They are built on three things: data, software, and compute power. My name is Krzysztof Ociepa, and today I will show you how we built our custom framework and use it on supercomputers located in Kraków in Poland to train our national language model called Bielik. Before we began working on Polish language model, I conducted my own research on language models. As part of that work, I implemented a simple training framework that was easy to modify and allowed me to train small language models on my card RTX 4090 with 24 gigabytes of VRAM. Using it, I was managed to train a 1 billion parameter model in just 44 days, literally under my desk. And surprisingly, its language was better than GPT 3.5, was more natural, richer, and more fluent. And please keep in mind, it was almost 2 years ago. Now, some of you might wonder, why didn't I use an existing framework? And the answer for this is simple and still true. Most of the frameworks are large, hard to customize, full of dependencies, and did more than necessary, which they made them usually slow. And my custom framework avoided all of that. It was light, fast, and efficient. In November 2023, I joined Speaklish, the Polish open source and open science project, where we collect data related to our language and our culture. And just a month later, Cyfronet, the Polish Academic Computer Center, joined us as well. And since then, Speaklish and Cyfronet have been collaborating on to build our national language model, Bielik. And from the very beginning, we decided to use my framework and develop it to train our models. But before I will tell you about our progress, let me share the challenges we faced. Scaling resources is not easy, especially moving from a single RTX 4090 to supercomputer with GH200s. And it introduced several problems around data management, performance, fault tolerance, and more. Another challenge was the limited availability of compute power, because even having access to supercomputers, we were able to use only 256 cards for our trainings. And with such amounts of GPU, training models larger than 7 billion parameters from scratch on several trillion tokens would take months. And finally, working with GH200s brought its own headaches. Installing software was not trivial, and we had to compile, build PyTorch and all dependencies ourselves, and sometimes it was a nightmare. Data for less popular languages like Polish is another challenge. High quality Polish text is scarce, instruction datasets in Polish are very limited. You cannot just go to Hugging Face, grab some nice dataset and use it in your training. And there was also lack of diverse benchmarks for test linguistic and cultural aspects. Our core team is small, fewer than 10 people, and we are responsible for a wide range of critical tasks, from data preparation, synthetic data generation, and quality assurance, to optimizations, training runs, and benchmarking. And it's truly a case of small team with big responsibility. To make it even more challenging, all of this work has been done pro bono without financial compensation in our personal free time after regular jobs. On this slide, you can see the timeline of Bielik model releases. Within 1 year, we published 3 major versions, what we call the Bielik trilogy. Achieving such rapid releases under the limitation of people, time, resources was not easy. But we made it possible because we know that quick and frequent releases are essential to maintain LLM relevance. You've heard about the challenges we faced, and now it's time to share you our solution. So our solution is built on 3 pillars: data, training, and quality. For the data, we collected over 3 terabytes corpus of Polish text and implemented a high-weight Python package to work on it with it. We also built a dedicated analytics dashboard with 120 data categories and quality metrics. For training, we developed our own framework with multiple optimizations at different stages. And finally, for the quality, we created an advanced data pipeline with a custom data quality classifier. We also developed 7 diverse benchmarks to measure different linguistic and cultural aspects, as well as a custom chat arena. And there is a lot to cover in all of those areas, but today I will focus on training part and share more about our framework and infrastructure. And our framework is called Allamo, and it's designed for training small and medium-sized language models. It's implemented in pure PyTorch with no dependencies to other frameworks, make it easy to modify and ideal for R&D. Allamo is optimized for fast and efficient training, whether on a single GPU or in distributed environments with DDP or FSDP. It supports pre-training, SFT, DPO stages, and includes many unique features. And the best of all, the code is open source and you can find it on my GitHub. Allamo comes with a rich set of features designed to make the training more efficient and flexible. It supports FSDP version 1 and 2 with both sequence and tensor parallelism, along with distributed checkpointing. With FSDP, we support CPU offloading for parameters, gradients, and optimizer states. There is selective gradient checkpointing and selective freezing to save resources. And training is highly customizable with hooks and on-the-fly modification of the configuration. So basically, you can run a custom script on an event during your training, an event like checkpoint saving or something. We provide weighted cross-entropy loss and adaptive learning rates. These two features were introduced during training of the first version of the Bielik model. Allamo supports multiple attention implementations and allows instruction packing with custom attention masks. For alignment task, we support the DPO with its DPO positive extension on multi-turn dialogues. And to track progress and quality, we have export metrics to. With Allamo, we provide a set of useful scripts for tasks such as import, export, to and from Hugging Face format, replacing or extending tokenizer, depth upscaling, or checkpoint merging. And we use these features and these techniques frequently in our models. As you can see, we merge 3 versions of our model, version 2, and to create a 4th one, which was the best. In general, we use merging technique heavily because we found it very effective for boosting performance, model performance. At the very beginning, we benchmarked Allamo against the popular Tiny Llama implementation, which at that time was claimed to have a very good performance. And as you can see, Allamo had better results. And it was the moment when we decided to use my framework for our trainings. Here you can see a performance summary of Bielik training on a GH200. Most of the time we train with 8K context window. And then at the end of the pre-training, we extended to 128K. And this approach is necessary because training on long contexts significantly slows down the process. For SFT, we use flex attention implementation because we employ instruction packing with custom attention masks, and flex attention provides the best performance in such setup. For DPO, we don't use packing and don't use torch compile. The input sequences have varying lengths, and iteration time is also fluctuating. That's why we calculated average time. Okay, so now let's dive into our supercomputers and see how we use them to train our models. On this slide, you can see the specification of our supercomputers, Athena and Helios. We use both of them for a range of tasks, from data cleanup and synthetic data generation to training and benchmarking. An important point here is that much of the software installed on these supercomputers is open source. And this slide compares HPC clusters with cloud environments for model development. At the user level, HPC provides non-root access and uses Docker containers. And the software stack is highly optimized, pre-built, and well-tested. HPC also offers dedicated help desks with experts familiar with the environment. And the data access is straightforward with large node shared file systems, including scratch spaces and long-term storage. However, running services like inference servers requires some special techniques like port tunneling. And setting up your ML stack on the HPC gives you a deeper awareness of software complexity and dependency management. HPC also provides tools and methodologies for performance profiling at scale. HPC clusters cover all major steps of model development. For data processing, they excel at tasks like deduplication, cleaning, classification, metric evaluations, all using high CPU counts, as well as scaling interference for synthetic data generation and quick tokenizations. HPC clusters for different training stages like pre-training, SFT, DPO, GRPO are very efficient thanks to GPUs and fast interconnects.